Their story is of epic migration, brutal destruction,
Uranus got jabbed and then knocked on its side.
of worlds more alive than anyone imagined. They hold the key to the history of the solar system and perhaps to life on Earth.
Uranus and Neptune are sort of the sentinels of the outer solar system. They're out past Jupiter and Saturn, well over like 2 billion, 3 billion miles from the sun.
Their size and location are a puzzle to planetary astronomers.
Uranus and Neptune are somewhat of a mystery because in a way, they shouldn't exist, or at least they shouldn't exist where they are.
Scientists can't understand how these giant planets grew so big, so far from the sun. The mystery starts 4.5 billion years ago with the birth of the solar system. In the beginning, the sun ignites from a disk of gas and dust. The rocky cores of the first planets start to grow. They collide with the debris in the disk as they orbit the sun. But the inner planets have a size limit. To grow into a giant planet, you need gas. Heat from the infant sun blasts these lighter gas molecules beyond a point astronomers call the frost line. Out here, it's cool enough for gas molecules like hydrogen and helium to stabilize. Jupiter and Saturn take shape first, sweeping in the abundant gas and quickly becoming gas giants. But Neptune and Uranus are different. Uranus and Neptune have less time to suck up as much hydrogen and helium before these gases disappear. But they're also forming farther out, where it's cold enough for other heavier gases to freeze. These are swept up by the growing outer planets.
Out where Uranus and Neptune are, tons of ice, tons of frozen gases as we might think of them, methane, ammonia, water. And so that's what makes up their composition predominantly.
They may be smaller than Jupiter and Saturn, but these heavy ices mean they grow dense. They become ice giants. But there's a problem. They're too big. The disk of gas and ice around a newborn star does not last forever. And material in the far reaches of the solar system is spread thin.
As you move further out in the solar system, the time scale for two bodies to find each other and collide and accrete slows down because the periods around the sun are much longer. It just takes a very, very long time.
Neptune and Uranus orbit the sun incredibly slowly, too slowly to collide with enough icy material to grow into the giants we see today.
So when we look at Neptune, and at this very distant orbit, we don't have enough time in the solar system to build a planet like Neptune. We just don't think we could build Neptune where we find it today.
So what happened?
It turns out where we see them now is probably not where they started out.
One thing we've learned about solar systems is that things are on a delicate balance, and planets migrate. They move around. They don't form in one place and stay there forever.
So what has enough power to move a giant planet like Neptune? An even bigger one, Jupiter.
One way for planets to move is by gravitationally interacting with each other. So they feel each other's gravity, they can tug, they can pull, and that effect can lead to planets slowly migrating around in their planetary systems.
The closer two planets are, the greater the effect. And in the early days of the solar system, the giant planets are much closer together. On top of that, they may have orbited in a different order than we see today: Jupiter, Saturn, Neptune, and Uranus. So what causes Neptune and Uranus to swap positions? The answer lies with Jupiter and Saturn. The two biggest giants lock into a gravitational dance.
There's always this interplay between them. Think of capoeira dancers balancing and moving together in a careful, orchestrated way.
Over millions of years, a rhythm slowly builds. These giants push and pull each other into more elliptical orbits. But the gravitational dance reaches a climax. The stretched orbits become unstable. The giants move off course. As Saturn and Jupiter twist out from the Sun, they fling Neptune out beyond Uranus. As Neptune moves out through the solar system, it pushes debris ahead of it. These are the leftover icy fragments from planet formation. Neptune snowplows these bodies out. They become the Kuiper Belt, the band of thousands of small bodies of ice and rock just beyond Neptune's orbit.
You can think of the structure of that Kuiper Belt as like blood splatter on the wall at a murder scene. It's the record of this really violent event of Neptune migrating outward across the solar system.
These ice giants are fascinating worlds, but they may be even more important than that. They might be the reason we're here.
Around 4 billion years ago, the young Earth is under threat from our solar system's bully, Jupiter. Positioned between the rocky inner planets and the giant outer ones, Jupiter dominates the solar system.
When you have a behemoth like Jupiter in your solar system, what it does determines in part what everything else does.
As Jupiter and Saturn lock into their gravitational dance, they migrate out, away from the Sun. Jupiter's immense gravity should pull Earth and Venus along with it. Earth and Venus's orbits should stretch and overlap with each other. It's a collision waiting to happen. Except it didn't.
So by the fact that we're talking about this here on Earth, suggests that Earth and Venus didn't have an impact early in the solar system when Jupiter and Saturn were migrating.
Something appears to have protected us.
Scientists think something yanked Jupiter into a different orbit before it had a chance to pull Earth and Venus on a collision course. But what could cause such a large jump in Jupiter's migration? This is where the ice giants enter the story.
Getting Jupiter to make a big jump in its migration is not easy. And so the best way that the models have been able to actually recreate this jump is to have Jupiter actually eject something the size of Neptune out of the solar system entirely.
Jupiter has a lot of gravity, and if you get too close to it, you're going to be accelerated as you fall in towards Jupiter. And it's possible that you can eject a planet completely out of the solar system this way. It's basically slingshotting it.
But a planet the size of Neptune is heavy, even for Jupiter, and slingshotting it out of the solar system gives Jupiter a kickback. Jupiter is knocked into a new orbit, and Earth is saved. But which ice giant sacrificed itself for us? Neptune is still in the solar system, and so is Uranus.
If you use computer models to basically predict the behavior of the planets, what you find is that if you start with Jupiter, Saturn, Uranus, and Neptune, you can't save the Earth without ejecting either Uranus or Neptune. But they're there, so we know that's not right. However, if you add a third ice giant, a fifth giant planet out there, then that actually makes everything work. You can save the Earth, have the planets in their present configuration, and that ice giant gets ejected from the solar system.
Imagine our solar system starting with 3 ice giants. One swings too close to Jupiter. Our solar system's bully throws its victim clean out of the playground. Jupiter is pushed into a new orbit by the ice giant's gravity. Earth is saved from Jupiter's deadly gravitational pull. And the solar system becomes the safe and orderly place we see today.
So we have a funny story here. This ice giant that may have existed billions of years ago yanked Jupiter back into the outer solar system, preventing it from destroying the Earth. But in the meantime, it sacrificed itself for us, getting ejected from the solar system. We have to thank it for our existence, but it's not there anymore.
We humans are really lucky. Had the dinosaurs not gone extinct, we wouldn't be here. Had this planet not been ejected out of our solar system, we wouldn't be here.
So where is this missing ice giant now?
The answer is pretty amazing. It could be clear across the other side of the Milky Way galaxy. The sun moves around the Milky Way galaxy at about 500,000 miles an hour, and in the history of the Earth, we've been around about 20 times. We could have lost that planet anywhere across the Milky Way.
But is this third ice giant really lost or just hiding? January 2016. Astronomers at Caltech make an astonishing announcement. They claim to have found evidence of a mysterious ninth planet disrupting icy bodies far out in the Kuiper Belt. Simulations suggest that if this so-called Planet 9 exists, it is similar in size to Neptune and Uranus. Could this be Earth's savior?
Could the solar system's primordial, missing, sacrificial ice giant be Planet 9? Yes, it could.
Perhaps this third ice giant wasn't ejected from the solar system after all.
One type of ejection is when you just take something and you throw it out of the solar system. But another, more gentle kind, is when you don't quite make it all the way out, and instead you go on a very, very long period orbit around the young solar system.
Planet 9 is thought to be so far out, it takes up to 20,000 years for it to travel around the sun.
Perhaps it's been observing the dramatic dynamical evolution of the solar system unfold from its frigid 20,000-year orbit.
Whether Planet 9 is a long-lost sibling or not, ice giants played a huge role in taming Jupiter. They made our solar system the haven it is today. But they are not peaceful places. Somehow, out in the deep freeze, Neptune is tormented by wild weather, mysterious superstorms, and maybe even diamond rain. Pluto used to be our most distant planet, until modern astronomers discovered lots of other icy objects orbiting alongside Pluto. And in 2006, poor Pluto got demoted. Pluto is tiny, smaller than our moon, and it's so far away, around 3 billion miles, that our finest telescope can pick out only a faint blob.
The very best images we've made of Pluto were with the Hubble Space Telescope. And the Hubble Space Telescope could only get about 20 pixels across Pluto. We knew that there were areas that were bright and dark, but we didn't know what they were, and it wasn't a very clear view at all.
This fuzzy image was pretty much all we had to work out what Pluto was like.
We knew that it had nitrogen ice on it, and we knew it had a moon, and we knew these other things. But still, you have to go there because it is so far away, 3 billion miles or more. We just had to go there to understand it.
Summer 2015. NASA's New Horizons probe flies past Pluto, completing a 9-year journey from Earth and recording the first ever close-up images of this most mysterious of worlds. Many scientists were expecting to find a flat, dead world, similar to our moon. But instead, the pictures reveal a world of dizzying diversity. High mountain ranges, winding glaciers, and vast, crater-free plains all hint at recent geological activity. Pluto, it seemed, was alive.
When we saw the first truly high-resolution images that revealed Pluto in all of its glory and complexity, It was an amazing emotional release for all of us on the mission team.
We suddenly got up this image that showed jagged mountains and totally bizarre hills and smooth plains and no craters at all on that particular image, showing that this really was a geologically youthful region.
Some of the features revealed by New Horizons defied simple explanation. One of the most baffling was a pair of vast mounds on the surface of Pluto, each topped by a deep depression. These mounds look just like young volcanoes, but how could that be possible on a planetary surface made mostly from ice?
Now, if you were to see something like that on Earth, you'd say, that's a volcano. If you saw it on Mars, you'd say, that's a volcano. You see it on Pluto, you think, what is this? There's nothing that can drive volcanoes on Pluto as far as we know. So what are these things?
The mysterious mounds on Pluto are huge, over 100 miles wide and around 3 miles high. To make sense of these perplexing formations, scientists turn to similar-looking features here on Earth. Planetary geologists like Janie Radabaugh call them shield volcanoes.
This volcano we're headed for is called Skjaldbreiður, and it means broad shield in Icelandic. Well, in some ways, it's sort of the eponymous shield volcano that we're about to land on.
Shield volcanoes are formed by long, drawn-out eruptions of runny lava, and they're said to resemble the shape of a warrior's shield lying on the ground. This one erupted just 9,000 years ago.
You can see giant crater right here, summit crater that's typical of shield volcanoes. And it's actually pretty deep right here, deeper than I expected. This is quite a young volcano, and so you can still really clearly see that crater. And actually, we see the summit crater on Pluto's shields very clearly. And that really kind of makes us really think they could be a shield volcano just because of it. Broad shape and a summit crater, just like this.
It's not unusual to find shield volcanoes on other planets. Mars, like Earth, is made mostly from rock, and it's home to the monumental volcano Olympus Mons, built up from vast eruptions of hot, runny lava millions of years ago. But lava is melted rock, and that's a problem, because Pluto should be too small and too far from the Sun to have anything melted. If its broad features really are volcanic, they must be made from something very different to lava. Janie Radabaugh believes the light color of Pluto's mystery mounds offers a crucial clue.
The kind of eruptions that make this shape a volcano are, hundreds or thousands of individual eruptions over time. They erupt out of the fissure and flow out across the surface, and then they just pile up on top of each other and continue to flow out, building up a broad shield over time. The same thing has happened on Pluto. It's just the lava that's erupted from Pluto doesn't look anything like this. It's not dark in color, it's not made of basalt. Instead, it's made of water ice.
Unlike Earth, Pluto has a surface of frozen nitrogen on top of a bedrock and mantle of solid water ice. But from time to time, some of this water ice must be melting to form explosive flows of liquid slush that spew out onto Pluto's surface just like hot, rocky lava does on Earth. The warm slush freezes rapidly on the surface, building up to form broad, icy shields just like the rocky shields we find on Earth and Mars.
If the water under the surface can be melted by something, some energy, it can burst through the surface and flow, just like lava does here on Earth. So instead of volcanoes like you have here, you get cryovolcanoes, cold volcanoes, on these more distant objects.
We have a myopic view of the universe, thinking everything has to be the way it is here. Here on Earth, volcanoes are hot. But on Pluto, volcanoes run cold, not hot.
But maybe the most exciting thing about Pluto's volcanoes is that they are virtually free from impact craters, meaning the warm slush must have flowed out of them really recently.
these features are very, very young. Pluto is active today. There hasn't been enough time for the bombardments of comets impacting Pluto to build up a record of craters on the surface. Pluto is active today. That's the headline.
Scientists expected Pluto to be heavily cratered, a geologically dead world similar to our moon. But when New Horizons flew past in 2015, it revealed a vast, heart-shaped icy plain, which appears much younger than the rest of the planet. And the western part of this plain, Sputnik Planum, was completely crater-free.
Of all the things that we saw coming back, the heart, Sputnik Planum, was the most surprising and the most interesting and the most sort of, oh, look at that.
The broad, pale surface of Sputnik Planum offers a window into Pluto's unexpected activity, because it looks an awful lot like icy glaciers do here on Earth.
There's not a crater to be seen anywhere across that surface. And that immediately tells us it's young. Some of the estimates are maybe as young as 10 million years, only since that stuff has been moved around and changed. That's today in geologic terms.
There's got to be something actively making that surface for it to be that smooth.
Something is regularly smoothing out the surface of Sputnik Planum. But what? Scientists can rule out cryovolcanoes. They make mountains, not plains. So what else could it be? The first clue comes from pale, snaking lines that appear to feed into the northern rim of the plain. These sinuous features look just like the rivers of ice that flow from mountainous glaciers here on Earth.
What we're looking at here is a massive glacier pouring out across a valley and emptying into a glacial lake. One of the first things we noticed when we saw the close-up images from New Horizons is not only a vast field of kind of a flat glacier, but also tiny little feeder networks into the glacier, like valley glaciers just like this one, emptying into the larger continental glacier.
Ices must be forming in Pluto's highlands and then flowing downhill into Sputnik Planum, just like outlet glaciers flow from high mountains here on Earth. But on Pluto, it's too cold for water ice to flow, so the outlets feeding Sputnik Planum must be filled with a very different kind of ice.
So the glaciers have to be made of things like nitrogen. Now, nitrogen is what makes up most of our atmosphere. It's a gas here. But at those temperatures, it freezes and becomes an ice, and a glacier of nitrogen.
We now think Sputnik Planum is a vast basin filled with frozen nitrogen and fed by mountainous glaciers to the north. This steady flow of fresh nitrogen explains why the edges of the basin are so smooth. But what about the regions that sit beyond the reach of the glacial flow? Something else must be wiping out craters in the middle of the basin. Jenny Radabov believes a weird pattern on the surface of Sputnik Planum suggests an astonishing possibility. Pluto's surface could be boiling.
Welcome to Sputnik Planum. I mean, really, this is what it would look like if we were standing on the surface of Pluto. You see a vast, flat glacier behind us, really white, extending off to the distance, and behind us, a ring of mountains. When we look at the surface of Sputnik Planum, we notice that there are regularly spaced cells, and they're a little bit rounded in the middle, they taper off at the edges, and they really have the appearance of something that formed by convection. So if you think about a pot of oatmeal, as it's boiling away, it's bringing material up to the surface and then it's kind of pulling it back down again at the sides, convecting over and over again.
The nitrogen ice of Sputnik Planum could be boiling like a pot of oatmeal, but so slowly the roiling surface appears frozen at any time. A similar but much faster process makes patchwork patterns in Earth's most active lava lakes. Hot globs of lava rise up, forming rounded cells on the surface. And cool lava sinks down, slipping between the gaps formed by the hottest bubbles of molten rock.
As we look at the surface of Sputnik Planum, what we're seeing is basically a lava lake in slow motion. There's material rising up and then moving over and descending again as it gets cool. And basically, if we could see that, if we could speed it up over a few thousand years, we would see individual cells all across the surface roiling and churning and boiling, moving, convecting nitrogen.
You really have to step back and realize just how amazing and weird this is. The temperature is hovering near 400 degrees below zero, and things are bubbling up and moving around. There's geology happening. What you have to remember is that it doesn't take a lot of energy to make something as cold as nitrogen ice flow.
But it does take some energy. And while Pluto wears its magnificent heart on its sleeve, a second, warmer heart must be beating deep below the surface. But out here, in the frozen expanse of near outer space, the question still remains: where's the heat coming from? "530 million miles from the Sun, a tiny lump of ice and rock starts its journey towards the inner solar system.
Scientifically, comets are more precious than pure gold. They are actual time capsules. They are preservations of what the chemistry, the environment was like when our solar system formed. And they hold clues as to how our chemistry arrived here on Earth. Comets are some of the most valuable scientific treasures that exist.
Finding a comet we can study is not an easy task.
Finding the right comet for a mission, it's kind of like you're auditioning them, right? One comes in and it's like, oh, that orbit's okay, but it's not exactly what we're looking for. And oh, this one's too big, this one's too little, this one's too active.
What we really want to see is that comet come from outer parts of the solar system and get heated up as it gets close to the sun, pass around the sun, and head back out to the outer part of the solar system. So you need to get way out in the solar system and catch a comet on its way in.
Comet 67P fits the bill.
The special thing about Comet 67P is how accessible it is here on Earth. It actually orbits around the sun once every 6.5 years. And its orbit doesn't take it all that far out, only about as far out as the planet Jupiter. That gives us many chances to actually reach the comet and successfully rendezvous with it.
67P's moment in the spotlight arrived. The European Space Agency launched the groundbreaking Rosetta probe.
For years, we've studied comets from afar. We had never seen one up close with cutting-edge technology to learn about how comets behave as they orbit the sun.
Missions to large planet-sized objects are hard. The Hubble Space Telescope's blurry images revealed Rosetta's target is just 2 miles wide. And not just a small target, a moving one. Comet 67P races through the solar system at over 33,000 miles an hour.
The precision involved is pretty incredible. It's like making that hole-in-one golf shot from New York to San Francisco.
But catching Comet 67P wasn't just a straight shot.
The spacecraft had to actually get the same sort of velocity as the comet, and with current propulsion systems, we can't achieve that by flying directly to the comet.
Instead, Rosetta performed a slingshot maneuver that would take 10 years.
So what it's doing, it's actually taking some energy away from the planet, so it's slowing the planets down a little bit and then imparting that energy into the probe.
Rosetta flew past Jupiter, nearly 100 million miles from the warmth of the sun, and entered the most dangerous part of its journey: hibernation.
Even though Rosetta had solar panels on it, it still had to be put to sleep. And the reason for that is that it had to track 67P a ways away from the sun, and there just was not enough collection area and solar power to be able to power the instruments.
It's normal to put spacecraft into hibernation, but the worrying thing at the back of your mind is that it had never been done for this long before.
31 months of hibernation gave Rosetta's team plenty of time to worry about what could go wrong.
It's dark and cold out there in space. There's a lot of things going on. There's a lot of little micrometeorites out there. And without the constant communication with that spacecraft, it just is a little nerve-wracking when the day comes and it's time to flip the switch and turn it back on.
January 20th, 2014. After almost 10 years in space, it was finally time for Rosetta to wake up, reactivate its communication system, and phone home.
I mean, the tension was just palpable. It was just, I mean, how long do we have to wait before we're going to get the signal?
It's got to work. It has to work.
Oh gosh, maybe it's just not going to turn on at all.
Have we lost the spacecraft? And then the peak appeared on the graph. It's like, yes, we've got contact with the spacecraft.
When I saw this comet, crystal clear, this mountain floating in space of ice and rock, my heart just dropped. They are some of the most dramatic, beautiful images I have ever seen.
And then as it got closer and we got to see more and more details on it, yeah, that's when things started getting really strange.
Quite simply, arrival at 67P, we expected to see something shaped like a potato, and we found something shaped like a rubber duck.
67P is no ugly duckling, but its strange shape created a problem for Rosetta. Orbiting the comet was going to be far more difficult than anyone had imagined.
A planet has a lot of gravity, so you can send the spacecraft out there and then just slow it down a little bit with a rocket burn and it'll drop into orbit. In the case of Comet 67P, you're dealing with a very small little rock. The spacecraft cannot feel the gravity of that rock, at least not until it's right up against it.
Well, the engineers had to actually plot triangular orbits. It was a very complicated set of maneuvers.
Once in orbit, Rosetta could start work. Its first task? Figure out how 67P formed.
So how did this comet get this weird shape? There's two main ideas. One is just that it was eroded somehow in the center. And so it started off as a more spherical thing and became the shape it is today through some unknown process.
The other idea is that it started as two separate objects.
Space rocks normally hit each other hard. They collide with an average impact speed of more than 11,000 miles an hour. That's 5 times faster than a rifle bullet. Was 67P involved in a pileup? A clue came from the distinct layers on the comet's surface.
The layers in Comet 67P are a little like the layers in an onion. If you see them aligned, that's a clue that perhaps the object formed as a single entity and only eroded later into its present form. But if you see those layers misaligned, like we actually do in the comet, that's a big clue that it started out as two separate objects, formed independently, sticking together to form the comet we see today.
The layers prove that 67P was originally two separate objects that fused together.
So as far as we can tell, these two separate bodies must have been formed in the same area. They're very similar in composition, but they are so light and fluffy that they would have destroyed each other if they had hit fast.
They had a low-speed collision and basically stuck together like two wet snowballs.
With one mystery solved, Rosetta began to investigate the chemical makeup of 67P. The little comet could answer one of the biggest questions in planetary science. From where did our blue planet get its water? 4.6 billion years ago, the inner solar system formed from a maelstrom of rocky debris. Temperatures were so hot, any water on the early Earth boiled away.
What the evidence suggests to us is that Earth's water arrived at Earth after the Earth formed. And the primary mechanism that we thought were responsible were comets.
You have to remember that comets are basically just big balls of ice and dirt. One of the main goals of the Rosetta mission was to analyze the water on this comet and see if it matched the water on Earth.
Comets come from two regions at the outermost reaches of our solar system: the Oort cloud and the Kuiper belt.
The Kuiper belt is in the plane of our solar system. And the member that most people are aware of is Pluto. But beyond that, there is a spherical distribution of icy bodies, the Oort cloud.
This is a repository of comets that extend for hundreds of thousands of times further away from the sun than we find the Earth. And it's kind of a big spherical cloud around the sun that's a kind of deep freeze for a bunch of big comets.
Billions of icy objects orbit safely beyond the chaos of the inner solar system, locking in primordial water. Astronomers believe that Comet 67P's former home turf was the Kuiper belt, until something sent it ricocheting inwards.
The influence of the gravity of Jupiter, because Jupiter's such a massive planet, it actually attracted the comet and pulled it into the inner solar system.
It slowly was perturbed and migrated into the inner solar system where we see it today. It's traveled, not just billions of miles in linear space, but really, when you think of all the orbits it must have made, just trillions upon trillions of miles, that's quite a journey for such a little object.
Now, 67P loops around the Sun in a 6.5-year orbit that travels as far out as Jupiter and closer in than Mars. As it gets nearer to the Sun, its frozen ice begins to heat up, leading to a famous effect: the comet's tail.
Sunlight comes in and heats up the comet's surface, and it gets transferred to the interior where there's a lot of ice, and the ice gets heated up and it vaporizes and makes its way to the surface. And once it's sitting on the surface, the solar wind is bombarding that comet, and it drags all of that material out into a long, beautiful tail.
Rosetta flew into the tail to analyze the water vapor. Its goal? Confirm it's the same type of water as we have on Earth.
Water does come in different flavors. And I don't mean salt water or fresh water. I mean what the water's made of, its molecules.
We're talking about the actual chemical makeup on the proton, neutron, and electron level. So you might have heard of heavy water before, and that just means that there is an extra neutron.
It's H2O, but one of the hydrogens has an extra neutron. So we call it deuterium. And so that water actually weighs more than normal water because of that extra neutron in the mix.
On Earth, there are roughly 160 molecules of heavy water for every million molecules of normal water. As Rosetta moved around the comet, it measured the ratio of hydrogen to deuterium in the water vapor. An exact match to Earth's ratio would confirm that comets were the source of our oceans. But Rosetta discovered something surprising.
What Rosetta found was that the deuterium to hydrogen ratio was 3 times that of the water in Earth's ocean. That means a comet like 67P couldn't have been the source of Earth's water.
If it was the same as the measurement of the ocean water, then we could have said that these comets could have been a delivery mechanism for the water that we see on Earth. The fact it was 3 times higher kind of indicates that comets like 67P were not the source of the water that we see on Earth today.
But although comets like 67P didn't deliver our water, we can't rule out all comets.
We have to keep this in perspective. 67P is but one comet. And what we know about objects like comets is that they come in families, and these families have different compositions. So it could be that some have Earth-like water, and those are the ones that brought water to Earth, and some don't.
I don't see wrinkles like this as going back to the drawing board. Sure, we get more questions sometimes than answers, but that allows us to probe farther and really expand our knowledge into how planets formed.
The composition of Comet 67P rewrites our understanding of the solar system. And the comet has more secrets to reveal.
The reason we went all the way out to Comet 67P and in fact the reason we study comets at all, is we're looking for clues about the origins of life.
As Rosetta examined the icy core of the comet, it found a treasure trove of molecules. Could 67P carry the building blocks of life itself?
We may owe our existence to the fact that comets billions of years ago came to Earth and brought the necessary ingredients for life.
They can also cause enormous destruction. Comets could kill us all.
If a comet were to hit the Earth, watch out. It would be a planet buster. It would be an object sufficient to wipe out all life as we know it on the planet.
Learn about comets, and just maybe we will learn how to survive them and begin to understand how the universe works.
When we study them, we're learning what the solar system was like when it was first forming, and we can learn about what other solar systems were like as well. And hopefully that will teach us a tremendous amount about how stars form and how planets form, and how comets themselves were originally formed.
Comets date back to the birth of our solar system 4.5 billion years ago. They were made by the same force that created the solar system, gravity. It began in a maelstrom of chaos. A giant cloud of gas and dust collapsed to form a whirling disk. Close to the sun, it was burning hot. But further out, it was cool enough for gas clouds to condense and freeze. Ice crystals fused with grains of dust. They slowly pulled together into larger and larger masses.
Over time, these sort of snowballed, like a snowball rolling downhill, picking up more and more and more material.
Eventually, they formed gas giants like Jupiter and Saturn. But not all the debris in the disk turned into planets. Trillions of lumps of dirty ice were left behind. The comets.
You could almost think of comets as sort of the frozen leftovers of the formation of the solar system.
They are almost unchanged to this day.
They're pristine time capsules, and if you could crack one open and see what was inside, you could literally see what the solar system was first made out of. That's remarkable.
But the comets did not stay put. Several 100 million years later, the solar system plunged into turmoil once again. Encounters with debris pulled the gas giants out of position. The giants' immense gravity then hurled comets in every direction, flinging trillions of tons of material from the dawn of the solar system into the cold outer reaches of space. Some comets settled in a region 4,000 million miles from the sun, the Kuiper Belt. But most were tossed even farther out, to form a giant sphere around the entire solar system. We call it the Oort cloud.
This is a region of our solar system that's farthest away from the sun. The sun is just a tiny little dot, one of many stars. And the whole area of space around you is virtually empty. There's nothing there, very little. And just occasionally you'll find the odd comet floating out there in deep freeze, cold, dark, and very much alone.
In this remote ice cloud, there are more than 1 trillion comets. They can take millions of years to orbit the sun. But they don't always stay here. The orbit of every comet is a delicate gravitational balance. The smallest nudge can tip the scale.
Most comets spend their entire lifespan billions of miles from the sun, motionless, inert, simply waiting for something to happen. But then, perhaps a random collision takes place. Perhaps a passing star nudges it, and then the gravitational force of the sun inevitably pulls it toward the inner solar system.
Gravity, the force that created the comets, then flung them to the edge of the solar system, now pulls them back in. Our comet begins its epic odyssey to spread life or death across the solar system. The smallest gravitational disruption can knock them out of their orbit.
It could be a nearby star going by. It could be us going through a denser part of the galaxy. Anything that just gives a little gravitational hit to a comet can cause it to fall in towards us.
Our comet has been disturbed. Now the sun's immense gravity takes over.
You can think of the gravity of our solar system sort of like being a hillside. At the bottom, there's the sun, and comets are way at the top of that hill. When they get dislodged, there's only one way for them to go. They have to fall down in towards the sun.
Our comet accelerates towards the sun, but its path is far from straight. Gravity from the planets can throw comets off course or out of the solar system completely. If they escape these obstacles, comets continue their journey toward the sun. Now they begin one of the most remarkable transformations known to science.
A chrysalis to a butterfly. They become the most spectacular things the universe has to offer.
As it passes Jupiter, our comet begins to change.
As it starts to move a little bit faster and starts getting closer and closer to the sun, and it starts feeling the heat of the sun, that's when things really start to change.
500 million miles from the sun, heat brings our comet to life. Frozen gases start to vaporize. Grains of ice and dust rise from the surface.
As the comet continues to approach the sun and gets warmer, more and more gas is released. The comet becomes a fuzzy ball. There's a solid part in there, but it's surrounded by a much larger sort of cloud of material.
This cloud of dust and gas forms an atmosphere or coma around the comet. And it also creates the comet's huge tail. It's all driven by the sun, and it's not over yet.
There's something called the solar wind. It's actually a huge wave of charged particles originating from the sun. This fills our solar system, and as a comet begins to move further and further in towards the sun, the solar wind gets stronger.
Like a cosmic hurricane, the solar wind blasts gas molecules from our comet out into space. They form a second giant tail.
The solid part of the comet might only be a few miles across, and the fuzzy part might be a few thousand or tens of thousands of miles across. The tail that gets swept back as that material is blown off by the solar wind can be millions or tens of millions of miles long.
Our comet hurtles through space at 50,000 miles an hour. It's about to enter the most violent phase of its journey. 200 million miles from the sun, water ice begins to vaporize.
The ground would start to shift and quake, and as the material beneath my feet is literally thawing, we'd have great big jets of carbon dioxide and water ice starting to come out. And that would not be a very good place to be standing.
The surface cracks open. Gases explode. Debris fires in all directions. The force of these eruptions makes the comet tumble erratically.
Every jet that turns on is literally like a little jet engine attached to the comet.
Like a dragster on a racetrack, our comet explodes to life. Incredible speed, irresistible energy, and a vast plume of debris. Our comet transforms into a cosmic hot rod. But speed and energy are a volatile mix. Our comet could blow apart at any moment. The cloud around our comet is now bigger than Jupiter. Its tail stretches for 100 million miles. An object 4.5 billion years old emerges from the dark.
Every arrival of a new comet is like a gift from the universe. We've never seen this little bit of the solar system before. This little building block, this little baby picture, it's completely new to us.
It's a chance to study the origin of our solar system. And what we're learning is a revelation. Comets are far more hostile and alien than we imagined.
One of the holy grails of comet science is to really understand what is in a comet's nucleus, what is actually on the surface, what is the chemical composition, what are the characteristics of the rocks and the materials, the volatiles that are on that surface.
The nucleus is the fundamental building block of the solar system that we as scientists really want to investigate. That's where the mysteries really are.
There have been more than a dozen missions to comets in the past 3 decades. Every one of them has been a revelation.
We've learned about the chemistry of them. We've learned about the physical interaction they have with the sun. We've learned about their physical surface, their terrain, and how they're different even if you were to go from one spot on a comet to another. So we're really learning that these things are worlds unto themselves.
Scientists thought comets were white, like a snowball. That changed in 1986. When the Giotto space probe beamed back these images of Halley's Comet.
For the first time in history, we had a snapshot of the very center of that comet that entered human history on many occasions, and we found a cold, dead world. We found an object shaped like a peanut.
Halley was no snowball. A thick layer of black dust covered its surface. There were pits and hills, and Halley was 9 miles long, far bigger than anyone expected. Scientists thought that all comets were the same. They were wrong. In 2004, the Stardust probe flew into the tail of Comet Wild 2 and captured thousands of tiny dust particles.
When Stardust brought those samples back on Earth, we realized that, in fact, every comet is a unique object. Just like every planet is different, it looks like every comet is different. It has its own history to tell. Different materials went into its formation, different heat sources were injected into its interior, different chemical processes and geologic processes occurred. Each one is a unique world waiting to be explored.
Some comets are truly strange. These are real images of Hartley 2, a comet so weird, it snows.
It's so strange. We were able to see that there are golf ball-sized chunks of dry ice that are following the comet around up to 1 million miles away from the nucleus. This thing is just making a big mess.
Hartley 2 is just amazing. It looked like you were in the middle of a snow globe and you shook it up and there are all these little things, kind of like flies buzzing around food, just kind of floating out there. It's just not right.
Hartley 2 is a hyperactive comet. It tumbles faster and spits out more debris than most others its size. Comets are alien worlds. On Comet Tempel 1, there are smooth plateaus, craters and cliffs 60 feet high. Layers of rock lie on top of each other like a stack of pancakes. Each comet seems to have its own unique history. Tempel 1 gave scientists their biggest breakthrough. In 2005, the Deep Impact Space Probe slammed a projectile into its surface. The explosion dug out a crater 150 yards across.
Talk about a spectacular 4th of July. I mean, can you imagine anything better? We actually blew a hole in a comet. I mean, that's got to be one of the more amazing things that NASA has ever done.
The material the impact ejected allowed us to see inside a comet's nucleus for the first time.
It was completely unexpected. We found things like rubies and peridot, gemstones, tiny little things inside the comet. And we found all kinds of organic molecules, the very sorts of things we're made of.
Scientists now believe that comets play a critical role in our universe.
Where do the ingredients of life come from? Where were they all mixed together? Where did all this liquid water come from? Comets could hold a key to understanding the nature of life itself.
But opportunities to study them up close are rare. Across the universe, comets cause massive destruction.
They could be moving 50 or more times faster than a rifle bullet. And you were talking about something the size of a mountain. So the amount of energy that this thing would release upon impact is devastating.
But they're not always destructive. They have another side. Scientists believe they can shape entire worlds. This is Titan, the largest of Saturn's moons. It's the only moon in our solar system with a thick atmosphere. Rivers and lakes of liquid methane cover its surface. Titan was transformed by comets. Radar images reveal a moon shaped by a blizzard of comets that rained down over millions of years. Each comet vaporized when it hit, releasing gases from inside its nucleus. Gradually, they built up a rich, organic atmosphere and this strange liquid landscape. Comets turned a space rock into an Earth-like world.
Comets, in some sense, are the ultimate engineers of the solar system. Cometary impacts could give us the chemicals which give us the atmosphere, not just of Titan, but even perhaps the Earth itself.
So if comets have the power to reshape entire worlds, what part did they play in the history of our own planet? To find out, we need to get closer to a comet than ever before. We need to land on one. In March 2004, the Rosetta mission launched.
The Rosetta mission is named after the Rosetta Stone because just like the stone gave linguists the keys to the ancient language, we're hoping that the comet will give us the keys to understanding the ancient solar system.
November 11th, 2014 will be a landmark in space exploration. For the very first time, a spacecraft will touch down on the surface of a comet.
Previous missions to comets were basically flybys, and they basically give us tantalizing evidence that there was a greater mystery yet to be solved. Now we're going to land on a comet. We're going to be up close and dirty with a live comet streaming through outer space. And this is unprecedented.
Rosetta is around the size of a car. It's flying through space at 20,000 miles per hour. It's heading for this. A comet with a nucleus 3 miles wide, orbiting the sun every 6.5 years.